All right. One more second. All right. All right. Okay. All right. Good evening. Good evening, all. We'll start. Am I clearly audible and visible? Working fine, right? Working fine, right? Okay. Right. See. So today, it's kind of a special day for your batch because we are going to start Unit 3, right? After finishing Unit 2, the largest session we had, mechanics. So today we are starting. We are to step into oscillations and waves, Unit 3, right? Unit 3, oscillations and waves, right? And today itself, you will be learning oscillations part, right? Today itself, you will be learning oscillations part. Oscillations, simple harmonic motion, that's the part. You have first Hooke's law, springs, spring constants, those are the things coming up, right? So first of all, I will brief you the gravity of the lesson in terms of marks, right? In terms of marks, right? Which means attainable marks, right? So as a heading, write down Unit 3, oscillations and waves. Unit 3, oscillations and waves. Unit 3, oscillations and waves. And first part is about oscillations. So today we will be starting the oscillations part. Today we will be starting the oscillations part, right? Unit 3 in our lineup. Unit 3 in our lineup. Oscillations and waves, right? Listen. So as a lesson, this is like this. The gravity in terms of attainable marks. First thing, when comes to MCQs, right? So usually from this part we are getting around 7 to 8 MCQs. That usually from this part, usually we are getting around 7 to 8 MCQs, right? 7 to 8 MCQs, which means minimum we have 7 marks here from MCQs, right? And then from structured essays, right? We have a definite structured essay. Right? That is usually essay number 3. That is usually structured essay number 3. Anyway, structured essay number 3 is on waves. Is on oscillation and waves, right? And one structured essay, that's a definite one from this part, right? And it carries 20 marks. 20 marks means that is 5 marks out of 100. 5 marks out of 100. And this is actually number 3. Usually number 3 can change. Usually it's number 3. And when it comes to essays, right? Again, we have a definite essay. Essay number 6, right? Essay number 6 is from oscillation and waves. One essay, so that stands for 30 marks. Out of 100, that is 7.5. right? Then the total allocation here is this. Total allocation here is this, right? Let me write this way. Total allocation here is 5 plus 7.5 plus 7, right? So that's basically 20%. That's basically 20%, right? So we call this a 20% lesson. We call this a 20% lesson. We have 4 20% lessons in our syllabus from all 11 units for 20% units, right? This is the second 20% lesson you are to learn. You are going to learn second 20% lesson, right? First one was mechanics, and second one is this, right? So if anyone needs this allocation, you can just have a sketch, right? So otherwise, we'll be moving. Because before learning the lesson, you must know the allocation. That's better. Right? And listen, so far in mechanics, now we have discussed about like aspects like vectors, disorder components, linear motion, projectile motion, circular motion, rotational motion, hydro aspects, right? Hydrodynamics and statics, right? Such ones. But here, under oscillations and waves, we will be basically looking at something you haven't seen before. I mean, until this point, because basically we'll be concerning on waves. We'll be concerning on waves, right? On waves, and you will be learning another new motion type also here. And today itself you will be learning it. That is called simple harmonic motion. That is actually the fifth type of motion you are going to learn, right? Simple harmonic motion is also connected to waves, right? Then that's why it is prior to waves as oscillations, right? So that's how this is going to go. So we'll be starting today from scratch, right? No knowledge is required, no prior knowledge, nothing like that, right? We'll be starting from zero, right? So if you are starting today as a fresh student, right? No worries. You can start from today itself and proceed in unit 3, right? Okay, then as the first heading, write down oscillations. As the first heading, write down oscillations. Oscillations, first heading. Oscillations. Oscillations. Write down. Right, listen. Oscillation means, listen, oscillation means any type of a motion, if it undergoes back and forth, if the motion occurs back and forth repeatedly, right? Now, as an example, say this motion occurs back and forth repeatedly, right? That's also a type of an oscillation. Let me show you another thing. Say this motion, this one, right? See, then say this is, assume this has a straight wire, right? Like a straight pen. Yeah, here. Say this one. Now, if this occurs back and forth, see, this is also an oscillation. It occurs back and forth repeatedly. Right? Something like that. And it's not the must to be hanging. If the motion undergoes back and forth, say an object is hung from a spring and we are giving a small displacement, then that object undergoes like this. No? It's also an oscillation, right? And even let's say we have type of a movement like this, see, back and forth. Kohomari make a back and forth somehow it should be back and forth repeated, right? Any back and forth repeated motion is an oscillation, and then looking at their special features, we will be categorizing oscillation into 3 categories, right? So first of all, in general, any back and forth repetitive motion, repeated motion is an oscillation, right? Write down below. Any motion undergoes back and forth. Any motion undergoes back and forth. Any motion undergoes back and forth repeatedly. Back and forth repeatedly. Any motion undergoes back and forth repeatedly is called an oscillation. Is called an oscillation. Is called an oscillation. Is called an oscillation. Right? Okay. Now, looking at the special features, we are going to categorize oscillations into three categories. Right? Looking at their features, we are going to categorize oscillations into three categories. Right? Let's see. First one. Write down periodic oscillations. Periodic oscillations. Periodic oscillations. Periodic oscillation, or it can also be said periodic motion. It was a power cut here. It's heavily raining. So now the power is gone. Now the power is, I think, invisible because of this spotlight here. Right? Let's see whether it's come back. Can you give me 1 second to check whether it's only this room or what has happened? It seems it's for the entire area. It seems it's for the entire area. Right? So let's see whether it's going to come back. The only issue I have is not the internet connection, but the laptop. Right? Laptop is, charge of the laptop is not enough to run this for 3 hours. I think when everything is connected to the laptop, camera and lights and everything is connected, no, then it's going to degrade the battery. I think in less than 30 minutes or something like that should be. Right. So you are lucky. Okay, right. You are lucky. So I was worrying about the power cut. I just checked around and the whole area is dark. So, okay. Anyway, it's back. All right. Let's get into the thing again. All good, right? My audio. Okay. Video. Right. Periodic oscillations. Listen. Periodic oscillations. Listen. Okay, listen. If any motion occurs repeatedly in same time intervals, right? If any motion back and forth, if any motion occurs back and forth repeatedly in same time intervals, that's called a periodic motion, right? So the keyword here is same time intervals. Right? So I'll be highlighting or underlining the keyword in each case, right? Then once I ask you to underline or highlight, underline that word. That's the main feature. We have categorized this motion type in oscillations, right? Write down below, under this one, under periodic, write down. If any motion occurs, repeatedly, during same time intervals, if any motion occurs repeatedly during same time intervals, it is called periodic oscillation. It is called a periodic oscillation. It is called a periodic oscillation. Right. As an example, listen. As an example, this is something you know. As an example, see. Say we are releasing a ball. Say you are releasing a ball onto this ground. Once the ball is released, so we know it's on the ground and then it bounces back and undergoes a motion again like this and bounces back again. So likewise, it keeps on bouncing until it is coming to a rest. It keeps on bouncing back and forth during same time intervals. Right? That's a periodic motion. As an example, write down. Bouncing of a ball. Bouncing of a ball. Released above ground. Bouncing of a ball released above ground. Bouncing of a ball released above ground. Bouncing of a ball released above ground. Right. So if needed, you can have this diagram. Right. Bouncing of a ball released above ground. Then number 2, harmonic oscillations. Number 2, harmonic. Harmonic oscillation, or that is also called harmonic motion. Harmonic oscillation, also called harmonic motion. Harmonic. Right. Now in this first one, underline no highlight same time intervals. In this first one, underline no highlight same time intervals. In the first one, underline no highlight same time intervals. Right. Now harmonic. Listen. Right. Listen. Now harmonic means if any motion occurs during same time intervals, right? Same time intervals around a common center, right? If it has a common center and if it occurs back and forth, that's called a harmonic motion, right? Now in this example, this doesn't have a common center because this amplitude, this height decreases bounce to bounce. Then there's no any fixed point as a center. But if any motion has a fixed point as a center, right, and it undergoes during same time intervals back and forth, that's called a harmonic oscillation, right? Now, simple pendulum means one such example, something like this, right? Simple pendulum, one such example. Harmonic. One common center is here, and around that common center, simple harmonic motion undergoes, right? Something like that. Harmonic oscillation, write down below. If any motion occurs, if any motion occurs repeatedly, during same time intervals, around a common center, it is called a harmonic motion. Around a common center, it is called a harmonic motion. It is called a harmonic motion. It is called a harmonic motion, right? So as an example, as I mentioned, right, example for this one is, listen, example for this one is large oscillations of pendulum, simple pendulum, like this. So you know simple pendulum, right? Large oscillations of simple pendulum, right? It undergoes around a point somewhere here, no? The point of it undergoes back and forth around this point, right? So that is a harmonic motion. That is a harmonic motion, right? As an example mention, large oscillations of simple pendulum, large oscillations of pendulum, large oscillations of pendulum, right? And take it down. Write down the diagram. So is harmonic motion a subcategory of periodic motion? Yes, exactly. That's a subcategory of periodic motion, right? So that's how I'm categorizing this one, right? Periodic, then under periodic we have harmonic. Under harmonic, again we'll have simple harmonic. That's how it goes. So then what is the third and fourth 20% lessons? Thermal and electricity. Okay, right? Then number three, here you have to, this one you have to underline or highlight a common center. Here you have to underline or highlight a common center. Or around a common center. Highlight around a common center. Right? Then simple harmonic. Third one, simple harmonic oscillation. Right, listen. So it is like this. Periodic cause if the motion occurs during same time intervals. Harmonic cause if the motion occurs during same time intervals around a common center. And simple harmonic is same motion means same definition so far, like during same time intervals around a common center along a straight line is called a simple harmonic. Simple means straight, right? The word simple means straight, right? We call simple linear motion for linear motion. Then what this word simple says is straight, right? Then in a simple harmonic motion, all two features here are also there, right? And other than that, it should be in a straight line. It should be in a straight line, right? Write down. If any motion occurs, if any motion occurs repeatedly, if any motion occurs repeatedly, right? During same time intervals, around the common center, along a straight line, around the common center, along a straight line, around the common center, along a straight line, around the common center, along a straight line. It's called a simple harmonic oscillation. It's called a simple harmonic oscillation, right? It's called a simple harmonic oscillation. It's called a simple harmonic oscillation, right? So in that definition, right, underline or highlight a straight line, right? Or along a straight line, underline or highlight along a straight line, right? So the keywords are periodic means same time interval, right? Here, same time interval, right? And here, around the common center, right? And here, along a straight line, right? So that's how these introductions are like adding up. Adding up means based on their specific features, these three are categorized. Now, as an example for this, right? One is if we consider small oscillations of pendulum, right? They are almost straight, no? Now, like this, if you consider small oscillations of pendulum, see, small oscillations. When the oscillation becomes small, this line is straight, that is approximately straight. But for large oscillations, that is a part of a circular motion. For large oscillations, that is circular. But for very small oscillations, very small in the sense, if the angle is less than 2 degrees, that is almost straight. So we consider this actually. We consider this as a simple harmonic motion. And other than that, say this mass is suspended by a spring. And we are giving a small displacement this direction, like this. Displacement means we are dragging this and released. Then it goes back and forth like this. Straight line around the center. That's simple harmonic. So likewise, these two are two popular examples, right? So any motion it has these features is a simple harmonic motion, right? So as examples mentioned, right? Mention both of them. First one, small oscillations of simple pendulum. First one, this one now. This one, small oscillations of simple pendulum. Right? Then as the second one mentioned, motion of a mass connected to a spring. Motion of a mass connected to a spring. Right? Take it down. Okay, right? Mention below in red, mention below in red, mention below in red. Only small oscillations in red, only small oscillations, only small oscillations of simple pendulum, only small oscillations, only small oscillations of simple pendulum, only small oscillations of simple pendulum can be considered as simple harmonic, can be considered as simple harmonic, can be considered as simple harmonic since large oscillations, since large oscillations, since large oscillations travel in a circular path, 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 right? Okay. So as one of you asked, now this is how these three motions are if I graphically represent this using a Venn diagram, right? Something like this. If you represent this using a Venn diagram, right? Now this is the oscillations, right? These are the oscillations, all types of oscillations, right? And this is periodic, right? And this is harmonic, right? And this is simple harmonic, and this is simple harmonic, correct? Periodic, under periodic, if there's a common center, that's harmonic, right? Then having both features, if it is a straight line, that's a simple harmonic, right? Then as a summary, this is what we can see. Take this down also as a summary. This is a Venn diagram. This is a Venn diagram. This is a Venn diagram. Okay, right. Let's move on. As a next heading, write down Hooke's law. Hooke's law. Hooke. Hooke's law. Right. Look at the board. I'll explain Hooke's law using a spring. Right. This is valid for elastic objects, right? And most common thing we will be using is springs. So I'll be explaining this using a spring. Listen. If no force is applied to a spring, applied on a spring, if no force is applied on a spring, right? If no force is applied, that is in its natural length, right? This is called the natural length. If no force is applied, look at the board. Look at the board. If no force is applied, we call this the natural length, right? We call this the natural length. When there's no force applied, natural length is when there's no force applied, right? Here there's no force applied. F equals 0. No force is applied. So spring is in its natural length. Let's assume this natural length as L. Let's assume its natural length as L, right? And then say a rightward force is applied to stretch this, then the spring is stretched. No, something like this happens. Spring will be stretched. Spring will be stretched, right? If a rightward force like this is applied, and this endpoint is here now, right? Natural length is only from here to here, right? And this additional length which was elongated is called the extension, right? This additional length is called the extension. This additional length is called the extension. Then this is an extension, right? We denote by x here in Hooke's law. We denote by x in Hooke's law, right? Sometimes E is also used, but the popular term here is x in Hooke's law, right? Extension. And if this kind of a force is applied, look at the board. If an opposite force is applied, this is going to be contracted like this. If an opposite force is applied, right? Then if the force is applied like this to this direction, if a force is applied to the opposite direction, now the natural length is from here to here, and now this part is contracted. That is also called E. That is also labeled as E. EOX. Abhi x ke lao. Sorry. EOX x, right? And this is called a contraction. This is called a contraction. This is called a contraction, right? For that also both x and E are used. Right now, two things. Listen. Two things. If no force is applied on a spring, it is at its natural length, right? So even if this force is removed, it is returning to its natural length, right? When this type of force is applied, as it is extended, right? This elongated length is called the extension. And when the opposite force is applied, right, this contracted length is called the contraction, right? Both are denoted by XOE, right? Take it down. Take it down. Take it down. It's raining heavily today. I mean, for this area. Stay safe these days because I heard about several dengue fever cases these days, right? Especially in Western Province, Colombo district and Kaludara district. Especially, I heard about several dengue fever cases, right? So be safe. Okay, write down below first point. Write down below first point. If no force is applied, first point, first point. If no force is applied, if no force is applied, if no force is applied on a spring, if no force is applied on a spring, if no force is applied on a spring, it is in its natural length. It is in its natural length. Natural length. It is in its natural length. Slash unstretched length. Unstretched. Natural length slash unstretched length. Right? Natural law unstretched. Natural length or unstretched length. Right? Next point. Next point. Next point. Difference in length. Difference in length. Difference in length. Difference in length from its natural length. Difference in length from its natural length. Difference in length from its natural length. When a force is applied, difference in length from its natural length. When a force is applied, when a force is applied, is called extension. Is called extension. Is called extension. Is called extension. Right? Now, even though this is a contraction, right? In general, we say extensions either way, right? For both sides, both directions, we call extensions, right? So that's why both are denoted by same XOE. XOE, extension. Either way, we call it the extension, right? But this is actually a contraction, that is also called an extension, right? Then look at the board. Look at the board. So what Hooke's law says is something like this. This applied force is proportional to extension, right? So what it says is the applied force is proportional to extension until the proportional limit. Proportional limit means it has a certain limit. If that limit is exceeded, if that limit is exceeded, it is not going to come back to its natural length, its initial length, right? So therefore, this is valid only in the range of 0 to proportional limit only, right? So we'll be seeing in-depth learnings and the features under elasticity also, right? That is our unit 10. Under unit 10 elasticity, you will be learning about like in-depth learnings, in-depth comprehensive parts about elasticity. Right now, here we have just about the proportional limit. Just about the proportional limit. Proportional limit means, right? If it is exceeded, it is not going to come back. Simple as that, right? Okay. Take this down in red. In red. Take it down in red. Right? Write down the law in red. Write down Hooke's law in red. Write down Hooke's law in red. Applied forces. Write down Hooke's law in red. Applied forces directly proportional to applied forces directly proportional to extension, directly proportional to extension up until up until proportional limit, 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 right? Okay, now look at the board. Then from Hooke's law we have this result. Look at here. From Hooke's law, right? We have this f proportional to x. To make this an equation, to create an equation, a constant of proportionality, a proportionate constant was introduced, and it is called k. So this equation is, final equation is f equals kx, right? And this is called Hooke's equation. This is called Hooke's equation. Is called Hooke's equation, right? Where F is applied force, right? X is extension or contraction, right? Both are called extension in general, right? And K, there are three meanings for K, right? There are three meanings for K, right? If there is a spring, it's a spring constant. If there is a spring, that's a spring constant. If there is an elastic material, that is called elastic constant. If there is an elastic material other than a spring, spring is a special case because it has coils. For any other elastic material, say this one was elastic string, then elastic constant, right? And there are cases without having none of them also. In such cases, K is called force constant. In such cases, K is called force constant. So there are three names. I have to know all of them. Right. Start from here, from Hooke's law, and prove the equation. Prove the equation. Right. F equals kx, Hooke's equation. Right. Hooke's equation. F introduced terms, F applied force, F applied force, F applied force. Then X extension, X extension, X extension slash contraction, X extension slash contraction, extension slash contraction. K, write down for springs, spring constant, for springs, spring constant, right? Then second one, for elastic material, that is called elastic constant. For elastic material, elastic constant. For elastic material, elastic constant. Right? Then none of above, force constant. Right? None of above, force constant. None of above, force constant. Okay. Write down below with a red pen. Write down below with a red pen. All the springs are solved. All springs are solved all springs are solved. All springs are solved using F equals kx only. All springs are solved using F equals kx only. All springs are solved using F equals kx only. Right? Okay, a small task. Listen, a small task. Find me the units and dimensions of a spring constant k. Find me the units and dimensions of k. A small task. Right? See? Then units of k is given by units of f over units of x. No? Right? Units of k is given by units of f over units of x. SI units should be substituted. SI unit of force is newtons. Extension is length meters. Then unit of k is nm minus 1. Unit of k is nm minus 1. Right? Dimensions of force over dimensions of extension. Dimensions of force mlt minus 2. Extension is a length L. Then L to L cancels. Then dimensions of k is mt minus 2. Mt minus 2. Right? We have another one having the same dimension in our syllabus. We have another quantity having the same dimension in our syllabus under unit 10, that is surface tension. Surface tension also has the same dimension mt minus 2. Right? Comparative things that is coming up in unit 10. Right? Okay, so before moving on to the rest, any questions so far? Anything to clarify from the things so far? From the discussed points so far? So you can quickly ask if anything. before moving on. Right. If no questions, we'll move on. As the next heading, write down spring systems. Next heading, spring systems. Spring systems. Spring systems. Spring systems. Right. Under that, number 1, when springs are in series combination. Number 1, when springs are in series combination. When springs are in series combination. Listen. A series combination means an end-to-end combination, which means if one end of one spring is connected to the other end of the other spring, like this, right? Such combinations are called series combinations, right? Now, in general, listen, in our syllabus, we have 7 equivalents, right? 7 equivalents, 7 types of equivalent combinations. And first equivalent you are going to learn in the syllabus is the spring constant. First equivalent, right? This is actually the first out of 7. You will be learning 7 equivalents, about 7 equivalents along the way, right? And in any type of a combination, if there is end-to-end connected, say resistors, if resistors are end-to-end connected, series combination. Say conductor rods, if rods are end-to-end connected, series combination, right? Wires, if end-to-end connected, series combination. So if anything is connected end-to-end connections, they are called series combinations, right? So let's consider 3 springs in series combination, right? See, let's consider 3 springs connected in series combination, right? To separate these springs, this dotted line is drawn to separate the springs, right? To us to see it properly. Right. Say a force F is applied for the system. A force F is applied for the system. And let's say their spring constants are K1, K2, and K3. K1, K2, and K3. Right? Listen. Equivalent means, listen, this is a general idea of any equivalent we have. Equivalent means the single unit to replace the system. Equivalent is a single unit to replace the system. And the equivalent should do everything the system was doing by its own, by alone, by the single unit, by the single equivalent. Right? Correct? In terms of everything, equivalent should be identical. And only difference is the system should be replaced by a single unit. Such unit is called the equivalent unit. Such unit is called the equivalent unit. Now, equivalent should be replacing the gap here. First thing, equivalent should be replacing the gap here. Right? Alone, single-handedly. This should be replacing the gap here alone. Then equivalent should be having this length like this. Equivalent is something like this, it's going to be. And if the force on the system was F, on the equivalent also, it should be same F. On the equivalent also, it should be same F. Right? Say equivalent K as KE, KE. Equivalent K, KE. Right. Now, look at the board carefully. Listen. We know, listen, we know when there's a joint, joint in the sense unbroken joint. In force equilibrium also, I have discussed about these things. When there is an unbroken joint, right, that joint should be in an equilibrium in terms of forces. Otherwise, if forces are different in the joint is going to break, right? Then if this force is F throughout this first spring, the force is F, and at this point it has a joint is unbroken. Then if this force is F, the equivalent opposite force should be there on the other spring at the joint. Otherwise, joint is going to break, which means forces along all three springs are same. It is F. Forces along all three springs are F. Forces along all three springs are F. Forces on all three springs are F. Right? We know F equals Kx. No? Hooke's law, Hooke's equation, F equals Kx. Now F is constant. F is constant. F is same for all of them. But K changes. Then when K changes, X must change. Since F is a constant. When K changes, X must change. Which means these three springs have different extensions now. Right? These three springs have different extensions now. Different extensions. Then let me mark these extensions as, right, X1, X2, and X3. And let's assume extension of the equivalent as XE. Right? And one more hint. Listen. One more hint. Always when you try to solve an equivalent, right, approach the question using the different quantity. Approach the question using the different physical quantity. Now in my case, different quantity is extensions. No? Then I'm going to approach this using extensions. Right? Now, total extension of the equivalent is XE. And extensions of these three are X1, X2, and X3. I told you already, this should satisfy everything the system was doing alone. Then we can say Xe equals X1 plus X2 plus X3. Right? Xe equals X1 plus X2 plus X3. Hereafter, what you have to do is use F equals Kx and substitute for X here and simplify. Substitute for X here and simplify after this. Okay, first of all, as row number 1, write down when springs are in series combination and take it down. Right? Time is what text source when introducing terms. Extension, no contraction. Extension, no contraction. How F is same. Unbroken joints. So if a joint is unbroken, should be same equal and opposite forces at the joint. Equilibrium of forces. Right? So it's forward in all of them. I haven't marked the force on the spring. That is the applied force. Right? That is the applied force. Applied force is same. On the spring it changes. right? At these joints it changes, at these joints it changes. Same value, directions are different. Right? X over 3. What is x over 3? We are finding equivalent k. We are finding equivalent k. Right? See? So we know f equals kx. F equals kx. Then x is given by f over k, no? Right? Then xc should be f over ke. X1 is f over k1, x2 is f over k2, and x3 is f over k3. F is common, f cancels. Right? Then 1 over ke equals 1 over k1 plus 1 over k2 plus 1 over k3. No need to simplify further. No need to simplify further. Right? We will refer the equation like this. If k is subjected, right? If k is subjected, you should be getting k1, k2, k3 over k1, k2 plus k2, k3 plus k1, k3. Okay. Right. Write down below in red. Write down below in red. This equation is valid for. This equation is valid for any number of springs in. This equation is valid for any number of springs. This equation is valid for any number of springs in series combination. This equation is valid for any number of springs in series combination. This equation is valid for any number of springs in series combination. Right? Okay, take this down as an example. Write down as an example. Write down as an example. Example. Write down. If simple n number of identical springs, write down. If simple n number of identical springs of spring constant k of spring constant k of spring constant k are connected in series combination. If n number of identical springs of spring constant k are connected in series combination, put a comma and find equivalent k for that series. Find equivalent k. Right? Springs and strings same, no, completely different. Right. Then 1 over k. 1 over k is 1 over k plus 1 over k plus 1 over k. This thing up to n. No? This thing up to n. Then n number of such terms are going to be added. N number of such terms are going to be added. Then 1 over k equals, if n number of terms are added, it is like this: 1 plus 1 plus 1 plus. So it is going to add up to n. It is going to add up to n, not plus n. Up to n. So finally it is n. 1 over k equals, then this is n over k. 1 is going to add n times 1, n. Then k, subject k, then k is equivalent, k is k over n. Right? So the equivalent here is k over n. Right. Listen, now from this, we can observe something. K over n, no? Then higher the number of springs in series combination, higher the number of springs in series combination. See, higher the number of springs in series combination, what happens is lesser the equivalent spring constant. Higher the number of springs in series combination, lesser the equivalent spring constant. Right? Lesser equivalent spring constant means, right? So what it determines is its stiffness. Right? Less stiff. Right? Less stiff means, right, it is much easier to pull. It is much easier to pull or push. Less stiff when k decreases. If k is higher, which means there is more stiff, then it is much harder to push or pull. Right? That's a practical idea here of the spring constant. Right. So after this one, mention this in red. After this one, mention this in red. In red, first point, higher the number of springs, higher the number of springs, higher the number of springs, higher the number of springs in series combination, higher the number of springs in series combination, lesser the equivalent spring constant, lesser the equivalent spring constant, lesser the equivalent spring constant. Higher the number of springs in series combination, lesser the equivalent spring constant. Within brackets, less stiff, less stiff, less stiff. Come on. Easier to push or pull, 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 easier to push or pull. Right, next point, keep using red. Next point, forces on each spring, forces on each spring, forces on each spring, forces on each spring are same, forces on each spring are same in series combination, are same in series combination, but extensions are different, but extensions are different, but extensions are different, but extensions are different. Right. Okay, then round number 2, when springs are in parallel combination. Round number 2, when springs are in parallel combination. Round number 2, when springs are in parallel combination. Parallel combination, right? Parallel combination is like this. Look at the board again, right? Look at the board again. Parallel means before the board. Look at here. Parallel means if similar ends are together, such connections are called parallel connections. Like this. See, all left ends are here, all right ends are here. All left ends are together, all right ends are together. Such connections are called parallel connections, parallel combinations. Right? If similar ends are together. Now here also, to connect springs, right? To connect springs parallelly, this is how we do, right? This is how we do. Like this, springs must be connected, and here also there should be a plate, a single plate to connect the springs. Otherwise, springs cannot be connected parallelly. Like this. Right? Now, let's assume the spring constants are K1, K2, and K3. And a force F is applied for the system. Force F is given for the system, applied for the system. Right? Now, if you think of the equivalent should also satisfy this gap, no? So, it should be between the same gap. Like this. It should be between the same gap. Right? A single one between the same gap. Like this. If the force on the system was F, force on this one alone should be F. Right? So, this is KE. Now, listen. Now, the thing is, since it is connected like this, all ends are together. Since all ends are together, right? When you apply a force, what happens is all these ends displaces together. all these ends displaces together, which means what is going to be equal? Which means the extensions are equal. They are going to extend together. They are going to extend together. Their extensions are equal, x. Their extensions are equal. Then what can we say about the extension of this one? This one. This should also be same. Whatever happens for the system should be same for the equivalent. Whatever happens for the system, right? It should be the same for the equivalent. X, right? Now again, go back to our equation. Go back to our equation. F equals kx, right? Now extensions are same. Extensions are same. Then when k changes, F changes accordingly. When k changes, F changes. Which means these forces are going to be different now. Then let's assume the force applied force on this one is F1, and on the second one is say F2, and on the third one say that is F3. Right? Now I told you last in the last question also, last question, last proof also, you have to approach by the different quantity. You have to approach from the different quantity. Right? Now the different quantity is being force. Then approach this from force. Since forces are different. Right? Since forces are different, then total force here, again force equilibrium, should be equivalent to F1 plus F2 plus F3. Right? So you know how to expand F and find K. Expand F and find K. Right? First take it down and find K again. The unstretched lengths are same. Yes, otherwise it cannot be connected. If unstretched lengths are different, we can't connect it parallelly. Right? We can't connect these two parallelly. If lengths are different, then by default, length should be equal to connect parallelly. right? We know f is kx, f equals kx. Then capital F is kex, f1 is k1x, f2 is k2x, f3 is k3x, right? Then x2, x cancels. K equals k1 plus k2 plus k3. K equals k1 plus k2 plus k3. So we'll be referring the equation like this. I write the equation. Right? Right. Write down below with a red pen. This is valid for. Write down below with a red pen. This is valid for. This is valid for. This is valid for. This is valid for any number of springs. Any number of springs. This is valid for any number of springs in parallel combination. This is valid for any number of springs in parallel combination. This is valid for any number of springs in parallel combination. This is valid for any number of springs in parallel combination. Okay. Now, as an example, write down again. As an example, write down. As an example, write down. If n number of springs, if n number of springs, if n number of springs of spring constant k, if n number of springs of spring constant k, n number of springs of spring constant k are connected in parallel combination, are connected in parallel combination, are connected in parallel combination, are connected in parallel combination. Put a comma and find k. Put a comma and find the equivalent of this series. Right. Right. Then n number of springs are here. K equals n number of springs. No? K equals then k plus, k plus, k plus, k plus. This goes up to n. Right. If k is taken out, then 1 plus 1 plus 1 plus. So likewise, it goes up to n. 1 is going to add n times. 1 is going to add n times. Then k equals, right, k times n. Then k is n k. K is n k. K equals n k. Right? K equals n k. Now, the observation here is higher the number of springs in this parallel combination, higher the equivalent. Higher equivalent means higher stiffness. Then that is much difficult to, much harder it to pull or push. Right? That's a practical idea. That's a practical idea. If we connect springs in series combination, it makes it easier to push or pull it. Right? If springs are connected in parallel combination, it is much harder, difficult to push or pull it. Right? Okay. Take it down. X equals x of n. What is x? Extensions are equal in a parallel combination. Extensions are equal in a parallel combination. Right, okay. Write down below with a red pen. First point. Right? Mention below with a red pen. First point. First point. Higher the number of springs in parallel combination. Higher the number of springs. Higher the number of springs. Higher the number of springs in parallel combination. Higher the number of springs in parallel combination, higher the equivalent spring constant. Higher the equivalent spring constant. Higher the number of springs in parallel combination, higher the equivalent spring constant. Within brackets, within brackets, within brackets, more stiff, within brackets, more stiff, more stiff. Come on, come on. Difficult to push or pull. Difficult to push or pull. More stiff. More stiff means that difficult to push or pull. Difficult to push or pull. Difficult to push or pull. Right. Next point, keep using red. Next point, keep using red. Keep using red. Next point. Extensions are equal in parallel combination. 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 But forces are different. But forces are different. But forces are different. But forces are different. But forces are different, right? Okay. So before moving on, any questions so far? Raise your hand if everything is clear up to this point, and you can send all questions if there's anything to know. If you need any clarifications, Now we are paving the foundation here. We are paving the foundation, right? Paving the foundation to get into simple harmonic motion, right? So again, we are paving the foundation. Okay. If no questions, let's move on. Right. If there are no questions, I will give you a question. Right. Right. There are no questions. I'm going to give you a question. Right. Take this down as a question. Take this down as a question. Take this down as a question. Write down. Find equivalent spring constant. Write down. Find equivalent spring constant. Find equivalent spring constant. Find equivalent spring constant. Find equivalent spring constants in given spring systems below. In given spring systems below. Right? In given spring systems below. In given spring systems below. Right? First one. You can take them down along with me. And then simplify one by one. Right. Try this 5. Try this 5. 5k over 2. So then x equals xn. xc and what is xc? What is xe and what is xn? Equivalent x. Everything is x. Everything is x. Total xn is an x. K 6k over 5. 11k over 3. Right, let's see. Try all 5. Try all 5. Combinations of springs. Right, combinations of springs. Okay, let's check the first one. First one, see, these two are parallel. The ends are connected together. No? These two are parallel, right? Then k and k plus k, no? That is 2k, right? Then for this part, I can simplify these two as, first we can simplify these two as 2k, k and k, right? 2k, then 2k, this resultant 2k here. There is an equivalent coming only for these two, no? The resultant 2k, that resultant 2k with this 2k are series, right? So if you really need the second diagram, you can have a second diagram, but not advised because these kind of questions are usually coming in MCQs, right? Then 2k and the resultant of these two is also 2k. Then 2k means we have to simplify 1 over, right? We have to simplify it 1 over. Then 1 over k a b is going to be 1 over 2k plus 1 over 2k, no? 1 over 2k plus 1 over 2k, right? Which means 1 over k a b is 2k, 2 over 2k. Subject kb, then kb is k. kb is k. Then final answer here is k. And without writing the simplifications, if you can simplify this at once, right, that is better. That is better because this is a MCQ question type. This is MCQ type, right? It's k. Second one. Second one. In second case, see, these three are, see, second case, these three are parallel. These three are parallel, right? If parallel, you can add them. K. Then this is going to be 3k. This is going to be 3k, right? If parallel, that is 3k. Then here 3k and 6k are series. Then that is 1 over 3k plus 1 over kv is 1 over 3k plus 1 over 3k plus 1 over 6k, right? Then common denominator here is 6k, right? Then 3 times 2 is 1 over kab. So kb means spring constant between a and b. Then 6k over 5. 6k over 5 is correct. So that is 6k over 5. 6k over 5. Right? Try all 5. Try all 5. What about third one? Third one. One says Rashi 4k over 3. Right. All of you can send answers if you got something, right? Then I know up to which level you have understood. Okay, what about the third one? Third one. 4k over 3. 4k over 3. Okay, good. Okay, now most of you have got answers. Good, very good. Right, good. See, third one. 2k and 4k. 2k and 4k means this is going to be 6k. This is 6k. Parallel, no? Parallel, no? Add karam 6k. Right, these two are also parallel. These two are also parallel. Right, 4k, 8k. That is 12k. That is 12k. Then 6k, 2k and 12k are in series combination. Then simplify. 1 over kb equals 1 over 6k plus 1 over 2k plus 1 over 12k. Then the common denominator is 12k. Common denominator is 12k. 6 times 2, then 2. 2 times 6 plus 6. 12 times 1. Right? So that is 12k over 9. KAB. Which means, I'll be writing here. Right? I'll be writing here. Which means KAB equals 12k over 9. 12k over 9. 12k over 9 is 4k over 3. 12k over 9 is 4k over 3. 4k over 3 is correct. Right? For third one, 4k over 3 is correct. Yeah, most of you have got good. Very good. Alright, then fourth one. I'll be raising the first one to do the fourth one. I'll be raising the first one. Right? Fourth one. These three are series. Sorry, these three are parallel. These three are parallel. Then 2k, 2k, 2k means k n means 2 nm minus 1. 2 to 2 means 6. Then here 3 and 3. 3, 3 means 6. And this is also 6. Then series 6 and 6. No? 6, 6 and 6. Then kb is going to be, right? If there are 3 springs of 6, which means 2 nm minus 1. 2 nm minus 1. Yeah, for fourth one, it's 2. 2 is correct. Right? 6, 6, 6. 1 over 6 plus 1 over 6 plus 1 over 6. Right? That is 2. Right? 1 over 6 plus 1 over 6 plus 1 over 6. This is the equation. This is the equation. 1 over AB is 1 over 6 plus 1 over 6 plus 1 over 6. Common denominator is 6. Then 6 over 3. 1 over KB is 3 over 6. So KB is 2. Right? Check your answers and make corrections. Next one. Are you still doing 5? Only one has shared the answer 5k. Try the last one also. Now, if any questions about first 4, feel free to ask, right? If you are all okay, go to 5 and try last one. Uh, 6K over 5, 6K over 5, 5K over 6, 6K over 5. Okay, see? Okay, you have done now. Let's see this one. So first of all, what I see is these two are parallel. See, first of all, these two are parallel. These two are parallel. These two are parallel. Then 3K means 4K, right? 3K and K means 4K, right? 4K. Then if these two are simplified, right? So if needed, this is how the diagram now is. Now the second diagram, I mean, second diagram. If these two are simplified, these two can be replaced by a single 4K, no? These two can be replaced by a single 4K, right? And we have another 4K here. It was given untouched, and this is a simplified 4K, right? Now, you can clearly see these two are series. Then 4K means 2K, right? 4K means 2K. Then finally, what you got is a 3K here, right? So finally, what we got is a 3K here, right? And a 2K here, right? These two, are 4K and 4K is 2K. Then finally we got 2K and 3K, 2K and 3K. That is 5K. That is 5K. How did you all got 6K or 5? Did I make any mistake? 3K and 4K, 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 2K, 2K and 3K. Parallel, 5K. I got 5K. Check your simplifications again. 5K. Isn't it 5K? The ones who got 6K over 5 or 5K over 6? You got 5K, good. Yeah, it's 5K. These two are parallel. Then 3K and K, it's 4K. 4K and 4K are series. 2K. Then 2K and 3K are parallel again. 2K, 3K parallel, 5K. It's 5K. It seems like 3 or 4 of you have done the same mistake. Otherwise, how could you get the same answer? 6K or 5? You have simplified these two 1 over. These two are parallel, no? If you put 1 over 2K and 1 over 3K, you will get 6K over 5. Right? But these two are parallel, not series. Okay, right? Make your corrections. Right. So raise your hand if everything is clear about these 5 examples I gave. And if any questions, quickly ask before move on. Clear. Right. Okay, then we are good to go, right? All right, then let's move on. Next heading. Stored energy. Next heading. Stored energy on a spring. 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 Write down below. Write down below. Energy stored due to. 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 An extension. Due to an extension. Energy stored due to an extension. Due to an extension of an elastic object. Due to an extension of an elastic object. Due to an extension of an elastic object. Due to an extension of an elastic object is called elastic potential energy. Is called elastic potential energy. Is called elastic potential energy. Right? So in mechanics, right, what we discussed was gravitational potential energy, GPE, gravitational potential energy. Now here we have elastic potential energy. Gravitational potential energy is due to gravity. That is due to gravity. Elastic potential energy is due to extension, elasticity. Right? That is due to elasticity, elastic potential energy. Right? So this is how it comes. Say extension of this spring is x. say extension of the spring is x and the spring constant is k, and the stored energy, elastic potential energy, is written as elastic potential energy B is written as half kx squared. Right. Take down the diagram and take it down. Take down the diagram and take it down. Write down the equation and highlight. What was the topic? Stored energy on a spring. Stored energy on a spring. Okay, right. So let's see an example. Let's see an example. Okay, write this down as an example. Example. Write down. Find stored energy. Write down. Find stored energy. Find stored energy. Find stored energy. Find stored energy. Find stored energy on each spring. On each spring. On each spring. Find stored energy on each spring and on system and on system and on system and on system below and on system below. Right, this one. First one. Within brackets, write down. Within brackets, write down. Within brackets. Given extension is within brackets. Given extension is write down. Given extension is 0.1 meters. 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 Right? Sorry. Okay, right? Stored energy on each spring. Stored energy on each spring and on the system. Stored energy on each spring and on the system. Na minus 1, sorry, sir. Na minus 1, sorry. Na minus 1. Okay, what about the first one? Right, for first one, if you do say that is E1 is then half kx squared. K of first one is 1. X is 0.1. Right, 0.1 means 10 to the power minus 1, no? Then squared. Right, then what's the value? This is 0.5, then 5 times 10 to the power minus 3 joules. 5 times 10 to the power minus 3 joules. Right, E2 for the second one, half into 2 into 10 to the minus 1 squared, that is 1 times 10 to the power minus 2 joules. 1 times 10 to the power minus 2 joules. Right, say E2. Then E3 for the last one, half 3 10 to the power minus 1 squared. That is 15 times 10 to the power minus 3 joules. You can also write it as 1.5 times 10 to the power minus 2. Fine. Right. Stored energies on each. Stored energies on each. For the ease of comparison, let me write everything with the same 10 to the power. Then this is same. 5 times 10 to the power minus 3 joules. Right. So you can also write this as 5 millijoules if needed. 10 to the power minus 3 is milli, no? 10 to the power minus 3 is milli. So this is 5 millijoules. And this one is 10 millijoules. And this one is 15 millijoules. Now it's more clear. 5 millijoules, 10 millijoules, and 15 millijoules. Right? And I asked the system. I asked that on the system also. Right? Right now, if you are finding the system, say E total, right? That is half. K of the system is 1, 2, 3 means 6, no? Right? 6 into 0.1 10 to the power minus 1 squared. Right? That is 30 times 10 to the power minus 3 joules, which means 30 millijoules. This should be equivalent to addition of these three, right? This should be equal to addition of these three because these are the stored energies on each of them. And then I ask the system, then it should be the addition. No, it's correct. 30 and 5 again 15, 15, 30. Right? If you add these three also, the same answer comes. If you add these three also, the same answer comes. Right? So get that idea. Stored energy in the system is the addition of energies of each. Both are fine. Either way, it's correct. Okay, finished, right? Let's try another one. As example 2, write down. Find stored energy. Example 2. Find stored energy find stored energy in the given system below. Find stored energy in the given system below. Find stored energy in the given system below. When an extension of 0.2 meters is given. When an extension of 0.2 meters is given. Right? Write down. Sorry, 2 nm minus 1, 2 nm minus 1. 1 nm minus 1. Right. Try this one. So one small change. This is 4. This is 4. Right. That's it. Right. 0.2 joules. Let's see. What about others? This will be the last example we'll do from this part before going to simple harmonic motion. So next thing coming up is simple harmonic motion. Right. See, first I'm going to simplify these two. Right. First we can do these two. 8-8 series. 8-8 series means that is 4. Right. And here 2 and 2 parallel. 2 and 2 parallel means 4. Right. Then here 4 and 4. 4 and 4 series means 2. Then here I have got 4. Right. And here after the simplification, right, 2 2 means 4, 4 4 means 2. This is 2. And here I have given you a 4. Right, parallel, then 4 2 4 here 10. So the equivalent is 10 ms minus 1. Equivalent is 10 ms minus 1. Energy, stored energy is half kx squared. Right, then half k is 10. Right, x is 0.2. X is 0.2. 0.2 means 2 times 10 to the minus 1 square. Right? Simplify. Then equals half 10 4 10 to the minus 2. Right? Then 2 times 4 is 2. Final answer. This is 10 to the minus 1, 0.2. 0.2 joules. 0.2 joules. 0.2 joules is correct. Yeah, 0.2 joules is correct. Right? Okay, say it again, and if anything, correct it. Okay, right? Okay. Shall we move on? Next heading. Write down. Next main part. Now we are going to step into the next main part. Right? Write down. Introduction to simple harmonic motion. 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 Right? We call SHM, simple harmonic motion. Within brackets, write down SHM. Introduction to simple harmonic motion. Within brackets, write down SHM. Right. So basically, you know what a simple harmonic motion is now. Right? Same time intervals, around a common center, along a straight line, those things are known. Right? But first, we'll see what the definition is. Right? And then I'll explain. Right? First, see what the definition is. So in definition, some other added parts are also there. Write down as definition. Write down definition. And write down below. Write down below in red. Write down the definition in red. Write down the definition in red. Write down. Simple harmonic motion is defined as. Write down. Simple harmonic motion is defined as. Simple harmonic motion is defined as. Defined as a periodic motion. Simple harmonic motion is defined as a periodic motion. Defined as a periodic motion. defined as a periodic motion which occurs back and forth, which occurs back and forth, a common center, 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 with an acceleration, with an acceleration, with an acceleration, with an acceleration acts towards center, 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 acts towards center, with an acceleration acts towards center is directly proportional to displacement measured from center, is directly proportional to displacement measured from center, displacement measured from center, displacement measured from center, displacement measured from center. Displacement measured from center. Right. So in the definition, I didn't say it's linear. Why? What's the reason? I didn't mention any word regarding linear. Linear ke lagi when why? What's the reason? What's the reason? Not to say it's linear. So we know simple harmonic motion is a linear motion. Simple harmonic motion is a linear motion. Simple harmonic motion is a linear motion. Circular path, then it cannot be a simple harmonic. Why I did not mention about linear motion here in the definition of simple harmonic motion? So in the initial introduction, I gave it as a straight line. Yeah, I used acceleration and displacement. Exactly. That's the point. I use two words, acceleration and displacement. Again, no need to say linear because they are linear vectors. Right? That's the thing. I omitted repetition, so I don't need to say it's linear again and again because I have mentioned about acceleration and displacement. Right? In the definition, underline or highlight these four keywords, these four phrases actually. Words name. Underline or highlight these four phrases. Underline or highlight these four phrases. Underline or highlight these four phrases. These are the keywords. These are the keywords, key features of a simple harmonic motion. It's a periodic motion about a common center, acceleration towards center, displacement measured from center. These last two are very much important for the proceedings. Last two are very much important for the proceedings. Last two are very important for the proceedings. Right. Now, stop all your work and look at the board. Stop all your work and look at the board. Right. Say, this is a simple harmonic motion about this point. Right. Say this is a fixed point O. We call center. This is a simple harmonic motion about this point. Now, what is happening is it starts from the center, right? And it is reaching a maximum point. It is reaching a maximum point, and then it returns. It is reaching a maximum point, and then it returns, right? And it happens. It occurs exactly on the same line. But if I draw like this, now you can't see the back and forth motions, no? So that's why I have kept a small space and I have drawn this, right? And then it goes beyond this point and reaching another point here, right? And coming back again like this, right? So basically, what's happening is now the motion is like this. See here, motion is like this about this point O. This is what happens. See, simple harmonic. All features that we know are there, right? All features that we know are there. Periodic, same time intervals, right? Periodic given. So that is in same time intervals, right? About a common center, about a common center, right? About a common center, and in a straight line, so all features are there. All features are there. All features are there. Then you can see the stop points. These 2 points are 2 stop points. They are instant stops. They are instant stops. And the motion continues like this, right? And for the ease of seeing this, I have drawn it like this, right? So first, take it down. First, take it down. And to mark accelerations and displacements, I will use a bigger means a magnified diagram. First, have this to identify points. This is called the center. This is called the center. O. This is called the center. And these two are called amplitudes. Amplitudes means maximum displacements. So at that point, the motion is going to stop for a moment and it's going to come back, right? Any this type of motion, any back and forth, any back and forth motion along the same line is a simple harmonic motion, right? But if I draw this like this, you won't understand anything. If I draw this like this with point O, like this, your pain. That's why I have drawn it like this. That's why I have drawn it like this with a small gap to understand the phases. To understand the phases, right? So label this. O is called center. O is called center, right? And A is called amplitude. A is called amplitude. What is amplitude? Amplitude means maximum displacement from center. Within brackets, write down maximum displacement. Maximum displacement from center is amplitude. Maximum displacement from center is amplitude. Maximum displacement from center is amplitude. From center is amplitude. Right. Look at the board. Look at the board. Now, I'm going to mark the directions of velocities, accelerations, and displacements in the diagram. Then for that, I need a kind of a bigger diagram now, a larger one. Then I'm going to use this for that purpose. Starting from here, let's say this is the center. Starting from here, reaching this point, using this the other amplitude like this, and reaching the other amplitude like this, and coming back, something like this. Okay, see, so this is one of the amplitude points. This is one of the amplitude points. Repeating again, everything occurs on the same line, but the only thing is to us to see these phases of the motion, right? There are 4 phases now. To us to see these phases of the motion, I have kept a small gap in between, right? Then starting from here, let's say t equals 0. T equals 0. It travels this way, right? From here to here. It stops at this point, right? It stops now, which means velocity exactly at this point. Velocity at this point should be 0. Momentary velocity. Instant velocity. Then it returns. Passing the center again. And passing the center, keep passing the center and reaching the other amplitude. Again, the velocity becomes 0. And directions are switched and reaching this point again. Once it reaches the center again, we call this as a complete oscillation. This is a single oscillation, a complete oscillation. So this is the periodic time for the whole motion t equals t. Right? Now, look at the board carefully. Tell me, now, first thing, if I measure displacement to a point somewhere, it should be measured from center. No? Then this is how displacement is measured. Displacement is measured from center. And now if you are measuring displacement to say somewhere here, again it's from center. That's how it measured. From center. Because it's going to look complicated. And now I'm going to mark the direction of velocity. Right. Tell me, when it is moving from this point to here, from here to here, this phase, it is traveling in leftward direction, no? Then velocity must be leftwards. So this velocity is leftwards, right? Look at here. This velocity is leftwards. Velocity is leftwards, right? Now here it is traveling from here to here, rightward direction, rightward direction. Then the velocity is rightwards. And here also it's traveling from here to here. So the velocity is rightwards. And here it is coming from this point to here again towards the center, velocity is leftwards. Right. Now about accelerations. About accelerations. Look at the board very carefully about accelerations. Right. Now, after starting from here, it is going to stop at this point. No? Now its target is stopping at this point. Then should it be accelerating or decelerating towards this direction? Starting from here and going to stop at this point. If it is going to stop here, it should be decelerating. If it is going to stop here, it should be decelerating. Then towards this direction, there is a deceleration. Then along the opposite direction, we can say it's an acceleration. Right? Towards this direction, look at the board carefully. Towards this direction, it is a deceleration. This is equivalent to an acceleration to this direction. Right? Then here, from amplitude to center, amplitude is at 0 and then velocity increases in this part. So it is accelerating, which means acceleration of this part is here, direction of acceleration is here. And again, at this phase, just after this point, its target is stopping at this amplitude again, other amplitude, right? Other amplitude again. To stop, again, it is decelerating towards this direction. So it is decelerating towards this direction, decelerating towards this direction, which means that is equivalent to an acceleration towards opposite direction. Right? So again, from this 0 to here, it is accelerating. So the acceleration is in this direction. Right? See, by definition, it says acceleration acts towards center. No? See, now whatever the phase it is, acceleration is always towards center. Whatever the phase it is in, acceleration is towards center. Right? It was there in the definition. So this is how you saw how that acceleration occurs. Right? This is how you saw. Towards center, this is also towards center, only 4 phases from here to here, here to this point, again center to amplitude, amplitude to center. Right? Now, take down this diagram, this one. Use colors if you need more clarity. Use colors if you need more clarity. Right? Just for now, until I prove this, keep this in mind. Maximum velocity of simple harmonic motion occurs at center. Right? You will be seeing it in the next part. Right? So until then, keep that in mind. Maximum velocity is at the center. Maximum acceleration is at the center. No. Maximum velocity is at the center. Right? About magnitudes, we will see in the next part. Take it down. Take it down. A whole different motion to all motions, all 4 motion types you have learned so far. A whole different motion for all 4 motion types you have learned so far. Okay, right. This is only one oscillation. This is called one oscillation. This one, this whole thing is called one oscillation. This is only one oscillation. This is only one oscillation. Right. Now, look at the board again. Look at the board again. Go to the definition. Go to the definition. It says something about acceleration and displacement. What is it? It says something about acceleration and displacement. From definition. From definition. It says acceleration is directly proportional to displacement. Acceleration is directly proportional to displacement. Then by definition, right? From definition, acceleration is, look at the board carefully. This is the best part here. Acceleration is directly proportional to displacement. Acceleration is directly proportional to displacement. But the thing is this, both are vectors. Listen, both are vectors. Acceleration is acting towards center and displacement is measured from center. They are opposite directions. No? Acceleration is towards center, displacement is measured from center. Opposite directions, right? So therefore, this is not just a proportional to x, then it should be a proportional to minus x. Minus sign refers to the opposite direction of both of them, because acceleration is acting always towards center and always displacement is measured from the center. Opposite, no? Always directions are opposite. Then that is a proportional to minus x. A proportional to minus x. Listen carefully. Now, to create the equation, to make this an equation, a constant of proportionality is added, right? And this constant of proportionality is coming from a mathematical result that is called differentiation. Now, after this point, we have to differentiate this. After differentiating, it comes. But in the next part, in physics also, you will see this up to some extent, how this constant comes, right? How this constant comes. This constant here is omega, right? This constant here is omega. Now, don't worry about how omega comes here. Omega is coming from circular motion, no? Right? We will see how omega comes here in the next part. That we have everything. Only the differential part is not here. Then this is A equals minus omega squared x. Don't worry about x at this moment, right? So you will be seeing the link, right? I will give you a hint. You will be seeing the link of simple harmonic motion with the circular motion next day when we are proving these equations. A equals minus omega squared x. Then final equation is A equals minus omega squared x. Right? This is called the general equation of a simple harmonic motion. This is called the general equation of a simple harmonic motion, where A is acceleration towards center, x is displacement measured from center, omega is angular velocity. That is a constant for any simple harmonic motion. That is a constant for any simple harmonic motion. That is a proportionate constant here, right? It's constant. It's constant, right? Take it down and introduce terms A, x, and omega. A, x, and omega. It's not a linear motion. It's not a linear motion. This is not a linear motion. Only the path is straight. Otherwise, this is not a linear motion. Path is straight. Right? So we will see all links with circular motions in the next part. Don't use the word linear motion because it's completely wrong. The reason is, now from the equation you can see the reason. Acceleration changes from point to point when x changes. In a linear motion, there's no such behavior. Here, acceleration changes from point to point when x changes, when it is moving from here to here. Acceleration changes from point to point. Right, okay. A. Acceleration towards center. Introduce. Acceleration towards center. A. Acceleration towards center. X. x displacement measured from center. X displacement measured from center. X displacement measured from center. Right? Omega angular velocity. Omega angular velocity. Omega angular velocity. Omega angular velocity. Within brackets write down. Within brackets write down. Constant for simple harmonic motion. Constant for simple harmonic motion. Write down within brackets. Constant for simple harmonic motion. Constant for simple harmonic motion. Constant for simple harmonic motion. Right? Then use a red pen and write down below with an asterisk mark. Use a red pen and write down below with an asterisk mark. Right? Use a red pen and write down below with an asterisk mark. Negative sign reverse to. Negative sign reverse to. Negative sign reverse to. Negative sign reverse to. Negative sign reverse to opposite directions of. Negative sign reverse to opposite directions of. Negative sign reverse to opposite directions of acceleration and displacement. Negative sign reverse to opposite directions of acceleration and displacement. Negative sign refers to opposite directions of acceleration and displacement. Right. Listen. Now, from this equation, we can see, right? If you consider magnitudes, listen. If we consider magnitudes, a and x are proportional, no? Higher the x, higher the acceleration. Then, which means acceleration at center is going to be 0. Acceleration at center is going to be 0. And the maximum acceleration occurs at amplitude. Right? If I consider only the magnitudes, look at the board again. A very good result again. If I consider only the magnitudes, considering magnitudes, a is proportional to x, no? A is proportional to x, right? And we have something here also. At the amplitude, velocity was 0. At the amplitude, velocity was 0, right? At the amplitude, velocity was 0. Amplitude is the maximum displacement. At the maximum displacement, velocity is minimum. Then, can you see that when it is decelerating from this point to this point, velocity decreases, but displacement increases. When it is decelerating from center to amplitude, displacement increases, but the velocity decreases, which means they are inverse. They are inverse, right? Which means displacement and velocity are inverse, right? Two things now. Acceleration and displacement are directly proportional, and velocity and displacement are inversely proportional. Now, I'm going to connect these all three. I'm going to connect all three. See, now, if A is proportional to X, and X is inversely proportional to V, this is the relationship all of them has among each of them, right? This is valid for any simple harmonic motion. Always acceleration and displacement are directly proportional, whereas velocity is inversely proportional, right? Now, we can see at which points, we can argue at which points maximum and minimum these quantities occur. Minimum displacement is at center. X becomes 0 because displacement is measured from center. Maximum displacement is at amplitude, right? Then maximum acceleration is at amplitude because X is maximum. Minimum acceleration is at center. Its value is 0. And when X is minimum, V should be maximum. Then when X is minimum, this is at center. Then at center, it has the maximum velocity. But when X is maximum, velocity is minimum. So at amplitude, it has the minimum velocity, 0. Right? Correct. First, take this down. Then we will see these features one by one. Take it down, starting from here. And after this, plot this variation also. Plot this variation between A and X for a simple harmonic motion. Plot this variation between A and X for a simple harmonic motion. Considering only the magnitudes written here. Keep direction aside for a moment to compare magnitudes. Keep direction aside for a moment and compare magnitudes. Negative means direction, no? Then keep it aside for a moment. Keep the direction for a moment. Keep it aside. Then think of the magnitudes. Sign is about the direction. That's a vector. What is the shape here? A and X. Straight line through origin. There are two types of straight lines through origin. Be specific. Right? A equals minus omega squared x. A equals minus omega squared x. Right? So x is our x variable. Omega squared is gradient minus this is y axis. Y equals minus mx. Right? So it is a straight line goes to center with a negative gradient. Y equals minus mx. Y equals minus mx. Right? Right? When you keep this in mind separately about the magnitudes and about the directions separately, right? Because we know directions of displacement as from center and acceleration as towards center, right? Okay. Then next heading, features of simple harmonic motion. 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 Right. Listen now. Listen now. Listen. Features, features of simple harmonic motion. Listen. Right. We'll be continuing the discussion on features next week, right? And for the parts we are going to learn next week, everything you have learned from the beginning is connected, right? So go through everything again and join the next class, because then you will understand everything perfectly, and by the end of the day, you will do all simple harmonic motion questions without any hassle. Otherwise, if these core concepts of simple harmonic motion are not clear, right, you will be stuck at the questions, right? These are the core concepts. These are the core concepts, and there are some more to come. Right? These are the core concepts, and in features, under features also there are some more to come. And once you understood everything properly, then easily we can tackle the questions. But if not, definitely you will get stuck, right? Everything is connected. Go through everything when you are joining the next class. And we'll be continuing from this point onwards next week. And any questions from anything we have discussed today so far? Any questions? Anything to clarify? Anything to know? Right, this is the 5th type of motion you are learning in your A-level journey. 5th type of motion. 5th out of 6. 5 out of 6. Right? Erasing this. Right. So how X is displacement from center? I thought it was extension, contraction. Extension and contraction is for springs. There's no spring here. Right? I didn't mention about any spring here. X is displacement. Notation is X. Notation is X. Right? Anything else? In simple harmonic motion, notation of displacement is X. In linear motion, notation of displacement is S. Right? To have a segregation between those two. Right? If you are using S, that is only for linear motions. If you are using X, that is for simple harmonic motions. For our is when we deal. Anything else? Clear. Okay, good. Anything else? Raise your hand if everything is clear about today. Clear, right? Good. Okay. So many more things are coming up, right? Many more things are coming up. So today we just got the start of this. You just stepped into oscillations, right? You just stepped into oscillations. That's it, right? We'll be spending coming 2 days also with simple harmonic motion. We'll be spending coming 2 weeks with simple harmonic motion, and then we are going to move on to waves parts, right? Oscillations part එක තමයි තාම we are still in the oscillations part, right? From the whole lesson, oscillations part is like 1/4, right? Sorry, 1/4 නෙමෙයි, 1/5. Oscillations part is like 1/5, and the waves part is like 4/5. We are in this 1/5 now. We are in this 1/5 now. Right. So I know you have understood everything today, but if you can't memorize this by the next day, right? If you are unable to memorize this by the next day, if you can't recall these things by the next day, again, you will be stuck somewhere. So please go through reminding again. Please go through before you come to the class, right? Mechanics is the longest. Mechanics is the longest. Right? Anything else? Right. Okay then. Then if no other questions, we'll wind up, right? And next week we are starting. Next week you are starting all the proofs of equations also. Proofs of equations means we'll be proving equations for acceleration, velocity, and displacement of simple harmonic motions. Right? 3 equations. Acceleration is already known. Now, make a acceleration equation. That's the same equation for acceleration. And there are 2 other equations coming for displacement and velocity also, because everything is different from any other motion. This is a very specific, unique motion we have, simple harmonic motion, right? All the features are unique features only for a simple harmonic motion. Then we have to prove equations for displacements, velocities, and everything, right? That's the thing. Then we'll start the applications also next week, right? After proving the equations, we'll start the applications also, right? Then we'll wind up. Stay safe and work hard. As I told you, now some dengue fever is also being viral around. Stay safe anyway, right? And rainy season is also started. I mean, it's raining for some areas. I don't know about your area exactly, but for some areas, yes, some areas in the sense, the majority of areas in the country will be affected by heavy rains in this weekend, right? Okay, then stay safe, work hard, right? See you in the next class. Good night and goodbye.